In this video, we'll be looking at ways to find the asymptotes of a rational function. Now, an asymptote could be vertical, like this line that I have here, graph approaching it like so, from one side, or it could come this way. But typically the graph approaches the horizontal or the vertical. Here's a horizontal asymptote, here's a slant or oblique asymptote. Typically the graph approaches the asymptote and does not touch it. For sure it's not going to cross or touch a vertical asymptote, because vertical asymptotes typically are defined from points where the rational function is undefined. Now the graph may cross a horizontal asymptote. So you might have something that looks like this. The graph may cross, say, right there, and then comes down and never touches again as x goes to infinity. So for horizontal asymptotes, we're concerned with the idea of what does the graph do as x goes to infinity or negative infinity. So typically if the graph approaches but doesn't touch the asymptote as x goes to infinity or negative infinity, then it's considered a horizontal asymptote. So again, the graph may cross a horizontal or oblique or slanted asymptote, but never cross the vertical asymptote. Okay, so let's look at the definition here. So we'll consider the rational function f of x equal to n of x over d of x. So typically a rational function is basically a polynomial over a polynomial. So here, in this case, the numerator defined by n of x is equal to this expression here. A sub n to the a sub n x to the n, a sub n minus 1 x to the n minus, and so on. And then for the denominator, the same thing. We're assuming now that the terms in the numerator and the denominator are in descending powers. So the highest degree term in the numerator is a sub n x to the n. The highest degree term in the denominator is b sub m x to the m. So that would tell me then that the degree of the numerator is n and the degree of the denominator is m. That's going to be important because basically the horizontal asymptote, the easiest way to get the equation of the horizontal asymptote is by using the degrees of the numerator and the denominator. So I'll put a note here. The degree of the numerator is n because a sub n x to the n is the highest degree term, and the degree of the denominator is m for the same rationale. Okay, so here's what we need to know. If n is less than m, then the graph of the function will have the horizontal asymptote y equal to 0, which of course is your x-axis. So that's saying the degree of the numerator is less than the degree of the denominator. So typically your most basic rational function would be something of the form, say, 1 over x. 1 over x. Now x over 1 is just x, so that would be a polynomial. So in order to have a rational function, if you have it simplified or reduced, you have to have an x in the denominator. So 1 over x would be a rational function. X over 1 would not. That would be basically a polynomial. Now, number 2 tells me that if the degrees are the same, if n is equal to m, then the graph of the function will have the horizontal asymptote a sub n over b sub m. So that means typically then, if these two exponents n and m are the same, you simply take the coefficients of these as a ratio and set it equal to y. That's going to be your horizontal asymptote. Now, if n is greater than or equal to m plus 2, that is the degree of the numerator, is 2 or more than the degree of the denominator, then the graph will have no asymptote, no horizontal, and no oblique asymptote. Number 4, if n is equal to n plus 1, that's saying the degree of the numerator is 1 more than the degree of the denominator, then the graph will have a slant or oblique asymptote. And the slant or oblique asymptote will have the form, and will basically look like this. It'll be y is equal to, say, mx plus b. The horizontal, of course, as indicated in 1, will have the form y equal to k, y equal to a constant. And for the vertical asymptotes, let's look at number 5. It says if d of k is equal to 0, that is, if the number k makes the denominator 0, so in other words, k is a 0 of the denominator, but k is not a 0 of the numerator, then the graph of the function will have the vertical asymptote x is equal to k. Now, if you have the rational function in reduced form, you don't have to worry about whether the zeros of the numerator are going to be or lead to vertical asymptotes. But if it's not, then you have to consider this. So any number that makes the denominator 0 but not the numerator will lead to a vertical asymptote. Okay, so let's look at the first example that I have here. Find the equations of the asymptotes for the given rational function. Okay, so you can see that for this one, it's in the form of the definition, the degree of the numerator is 1, because the exponent there is 1. There's only one term. The highest degree term in the denominator is x squared, so the degree of that denominator is 2. 1 is less than 2, so as far as the horizontal asymptote, we're going to have y is equal to 0. Now, for the vertical asymptote, so what did we say? The vertical asymptote will come from numbers that make the denominator 0, but not the numerator. So look at the denominator, it's x squared minus 9. So this factors into x minus 3 and x plus 3. So the numbers that make it 0, that is the zeros of the denominator, x equal to 3 and x equal to negative 3. Those numbers do not make the numerator 0. So x equal to negative 3 and x equal to 3 are the equations of the vertical asymptotes. So basically this video is focusing just on the asymptotes. So the answer then would be y equals 0 is the horizontal, x equal negative 3 and x equal to 3 are the equations of the vertical. So if you were going to graph this, you can easily graph this by simply using the location of these asymptotes and the intercepts. Okay, so if I say what is the x-intercept for this function, remember you find the x-intercept by replacing the x by 0. So if I replace the x by 0, because I put a 0 here and a 0 here, I get 0 over negative 9, that's 0. So 0, 0 is an x-intercept. So if I said, okay, what is the y-intercept? Well, you find the y-intercept by replacing the y by 0 and then finding the value of x. So if I put a 0 here, I want to know when is the expression on the right equal to 0. Well, because it's a fraction, the only way a fraction is going to be 0 is if the numerator is 0. So that means that x has to be 0. So y is 0, x is 0, so the x-intercept is 0, 0, but so is the y-intercept. The y-intercept is also 0, 0. So if I wanted to graph this using those values, okay, right here, the origin is where the graph crosses the x-axis. And let's say this is I go 3 units this way, I draw the equation of the vertical asymptote. Normally this will be dotted, okay? And then 3 units on the left to the negative side, this would be the equation of the other vertical asymptote. And then you can determine what the graph's going to look like by simply determining the sign of the function for values in between these intervals. So if I look at the values to the right of 3, say 4, and put it into the function, that'll be a 4 there and a 4 squared at 16 minus 9. This will be a positive. So this would tell me that the graph is above the x-axis to the right of this line. Okay, but since I have a vertical asymptote there and the x-axis is a horizontal asymptote, I would expect the graph, without plotting any points, I would expect the graph to go something like this. Okay, approach the vertical and approach the horizontal. Okay, now in between the negative 3 here and the positive 3 over here, if I pick, say, a 1, let's look at this interval right here between 0 and 3. Let's pick a 1. So if I put a 1 where the x is, that's going to be a 1. 1 squared is 1. So that's going to be 1 over negative 8. That's going to give me a negative. So in this interval from 0 to 3, the graph stays below the x-axis. So that means the graph has to come something like this. Okay. Now, in the interval from, say, negative 1 over here to negative 3, or from 0, I should say, to negative 3, let's pick a negative 1 and see what the graph does there. Put a negative 1 there and a negative 1 there. This time I have a negative 1 over a negative 8. That's going to be positive. So in that interval, the graph is going to go up. Since I have a vertical asymptote, I draw the graph so it approaches that asymptote. Okay. Now what happens to the right of the negative 3? Okay, so let's pick a negative 4 somewhere over here. There will be a negative 4 here. This will be 16. Negative 4 squared is 16 minus 9. That's going to be a positive 7. And then a negative 4, that's going to give me a negative. So the graph is going to stay below the x-axis, but since I have a horizontal and a vertical asymptote, I draw the graph so it approaches both in that interval. And that's what the graph looks like. Okay, for that, basically all I plotted was 1 point, the origin. 0, 0 is the x and the y-intercept. And I mentioned a while ago that a graph may cross the horizontal or the slant or oblique asymptote, but it will never cross the vertical because those occur at values where the function is not defined. Okay, so this is an example where the graph crosses the horizontal. Notice it crosses right there at 0, 0. But why is this considered a horizontal asymptote? Because it fits the definition. As x goes to infinity over here, the graph gets closer and closer to the x-axis but never crosses. Over here on this side, even though it crosses here again, on the far left, on the negative side, as x goes to infinity, the graph approaches the x-axis but doesn't cross. And how do I know that it doesn't cross? Because I only have one x-intercept. That's 0, 0. Okay. Now, if I were to do this on the graphing calculator, okay. Okay, let me clear this one. I have them all entered, the ones I'm going to be doing. So let me do the one that I just went over. Do a zoom 6. And then you have it. Doesn't give you the complete, but you can see here here it appears like it's not connected, but it is connected. It comes in this way. Let's try another zoom here. Let's try this number 7, see if we get a better look at the graph. Okay, so the z-trig that is normally used for trig functions gives me a better look at the graph. So you can see that it does have asymptotes right here and here at -3 and 3, crosses the origin here, and it stays below the x-axis in this interval here, above here in the next one, below in the next one, and above. And if you look at the table, you can see some of the values. So 0, 0 is the intercept. Look, number 3, you have an error. That's because you have a undefined. So that's where we have the vertical asymptote. I go to -3 again and have an error, or it's undefined there. And there you have it. Okay, so you can get the graph that way. The focus here, though, is simply on the asymptote. So the next one, want the equations of the asymptotes. So for the horizontal asymptote, we look at the degree. So the degree of the numerator is 1, x to the first, highest degree term. Denominator degree 1, again x to the first. So based on the statements that we just went over, the horizontal asymptote should be y equal to the lead term coefficient here over the lead coefficient over here. That's 1 over 1. So this is going to have a horizontal asymptote at y equal to 1. For the vertical asymptote, those come from values where the denominator is 0, but the numerator is not. Okay, so the denominator is 0 at 2, and the numerator is not 0 at 2. So that qualifies as a vertical asymptote. So you can graph this manually without using the graphing calculator, again by using the vertical asymptotes, finding your x-intercepts, the y-intercept, and determining the sign of the function on each of those intervals, and you can get a nice graph. But again, just to show it to you on the calculator, let me deselect this one. And again, let me try zoom 6. Okay, so there you have it. Okay, so this one shows you the vertical asymptote, which is at x equal to 2, right there. And then the horizontal asymptote comes right in here at y equal to 1. So if I draw it in there, it'll go right through there. Okay, let's go to the next one. Let me clear this one. Okay, now this one here, if I were just to look at this, the degree of the numerator, is 2. The degree of the denominator is 1. So the numerator has to be 1 more than the denominator. So I'd expect to have a slant asymptote. But keep in mind, this one is not reduced. So let's look at this a little further. The denominator is 0 at 3. So we would say, okay, x equal 3 would qualify as a vertical asymptote. But notice, if I put it 3 where the x is, 3 squared is 9, 9 minus 9 is 0, so that numerator is also 0. So that's not going to work, okay? Because the asymptotes come from numbers that make the denominator 0, but not the numerator. So basically what you have to do here is reduce it. This one factors, the numerator factors into x minus 3 and x plus 3. and I have an x minus 3 in the denominator. Okay, so these cancel out. The x minus 3's cancel out. So this then actually reduces simply to x plus 3. And I don't need it in parentheses, but I'll leave it like that. But remember here, since I divided out the x minus 3, I can only do that assuming that x does not equal to 3. Okay. Rational function is defined for numbers that has domain rather for numbers that do not make the denominator 0. So x not equal to 3 is not in the domain. So basically this is just a line. X cannot be 3. So notice if I replace the x by 0, I get 3. See, if I replace the x by 0, I get 3. If I replace the x by 1, I get 4. So if I were to plot those points and draw, this is a first degree function, so that's a line. So basically this is not a rational function at all. It's a line with one point deleted. Well, what point is deleted? Well, x cannot be 3, but if I were to put the 3 where the x is, I would get 6. So basically it's a line with a point 36 deleted. Okay. So over here then, let's look at the graph of this. Select the graph. Okay, so I'm going to select it. Okay, so it's a line. Okay, without even reducing it, I can enter in the calculator, and the calculator will give me the graph. And then just to confirm what I said, if I go to the table, notice the calculator tells me that for this line, x cannot be 3. When x is 3, I get an error. So basically, it's a line with a point 36, with a point 36 deleted. Okay. So let me clear this. Go to the next one. Okay, so let's look at this one. F of x is equal to x squared minus 2x minus 7. Okay, the degree of the numerator is 2. The degree of the denominator is 1. So 2 is 1 more than 1. So this one looks like it's going to have an oblique or slant asymptote. X equal to 1 makes the denominator 0, but if I put a 1 where the x is in the numerator, 1 there and 1 there, that doesn't give me 0. Okay, so in this case then I would expect to have a vertical asymptote. So this one's going to tell me then that I have a vertical asymptote at x equal to 1. Now, I mentioned then it has an oblique because the degree of the numerator is 1 more than the degree of the denominator. So it will have an oblique asymptote. So how do we get the oblique asymptote if we have one? So again, if the degree of the numerator is 1 more than the degree of the denominator, we have an oblique or slant asymptote. Well, what you do is you divide the denominator into the numerator. You can use synthetic division. So here I have the synthetic division using the coefficients here of the function 1 minus 2 minus 7. Okay, I'm dividing by the binomial x minus 1. So I put a 1 right here in this table. If I were dividing by x plus 1, then it's the opposite. This would be negative 1. And then basically the synthetic division procedure simply tells me this 1 is brought down over here, and I multiply 1 times 1. I get 1, bring it over to the next column. Minus 2 and 1 is negative 1. Multiply then by 1 again, times negative 1, bring it into the next column. I get negative 1, negative 7, and negative 1 is negative 8. Okay, so this is my quotient x. This is x squared here, so this reduces by 1 because we're dividing by power of x to the first. So this becomes an x and this becomes a minus 1. So if I were to set this up, then this would tell me that f of x is equal to x minus 1 plus negative 8, which is a remainder, over the divisor x minus 1. Okay, so in other words, if I put this back together, then I get the original function. Okay, but here's what we have to realize. As x goes to infinity, this denominator gets real large. So this term right here goes to 0. So I'm left with x minus 1. So this would tell me then that as x goes to infinity or negative infinity, the graph approaches the line x minus 1. So this would tell me then that the slant, or also called oblique asymptote, is y equal to x minus 1. So basically what you want to know then, if the degree of the numerator is 1 more than the degree of the denominator, you're going to have an oblique or slant asymptote. So the way you do it, what they tell you is go ahead and divide the denominator into the numerator, disregard the remainder because of what I just said here, and then you take your partial quotient, which in this case is x minus 1, set it equal to y, and that's your oblique or slant asymptote. Now if the degree of the numerator is 2 or more than the degree of the denominator, then you won't have a oblique or a horizontal asymptote. Okay, so let's look at what the graph of this would look like if you were to do it in the calculator. You can do it also using the technique I went over a while ago, but here's what we have. Okay, so now need to deselect this one. Select this one. And then do a zoom 6. Okay, so that's what the graph looks like. So here's my vertical asymptote x equal to 1. And then the slant asymptote or oblique asymptote goes this right through here, right here and here. Okay, this concerns or concludes the video. If you have any comments, please post them. If you have any suggestions or you want to see other types of examples related to this, just let me know. And if these are helping you, please subscribe, and we'll see you in the next video.